I'd like to start by thanking Anna for stepping in for me yesterday. Had a cold and couldn't make it, unfortunately. So I'm going to talk a bit about some of my recent work on this chromium-ytterbium system. As you all know, chromium is a very high spin atom, and what I'm looking at is the possibility of forming molecules involving this high spin atom. This is with two of our chairs. The brief outline on to give some motivation, talk about this spin-spin interaction, which is hopefully going to help us here. Then talk about resonances, then we probably won't get to the hyperfine. So we've already heard some motivation this morning about why you might want molecules with spins. One thing we can do, we've got this classic work by McKenny about using these spins on a lattice to look at various condensed matter systems. There's also proposals for using quantum information and computing, and we've just heard quite a lot about why you might want molecules of this kind for high precision spectroscopy and various things. This isn't so much my area, so I won't go into details, but we've heard some very nice talk. So what systems are available that have both an electric and a magnetic spin? Obviously, the ground state half-life dimers are out because they're singlets. So we can't use a system that we've been working on for 15 years in this field now. 15 years since the first molecule? Closely. There's some other options. There's a number of people in this audience who have worked on these applied single test systems, who will all know how hard these are, and it's very challenging resonance. Of course, there's been excellent progress on these. We've just heard some very interesting stuff about laser cooling molecules in progress. I've framed this in collisional terms with we've heard the spectroscopy side this morning, and some of the challenges in cooling heavier molecules. And I think we'll also hear some more about triplet alkali dimers later today. But these are inherently unstable molecules, they're not in the ground state. And they also are very weakly bound, having very small electric dipoles. And also all of these are all small spins. We've got doublets. I think all the laser cooled molecules so far they're all doublets as well. So far as I'm aware, there are proposals to do laser cooling of higher spin molecules. And so what do we want high spin molecules for? Naturally, some speculation here. The first thing is we just have a bigger spin. Is this just better for all the existing proposals? And two other speculative ideas touching on we just saw is this is, as Tim said, this is for dysprosium, but if we have two magnetic dipoles, do we get an even richer phase diagram? Do we get even more interesting and complicated phases? And something we're going to hear about later is synthetic dimensions proposed for molecules and for high spins. And if we bring the two together, can we get even more dimensions, or can we use these to enhance each other? As I say, these are speculative, but hopefully there are some uses for these kind of high spin molecules. It's also a good time to mention that you can do very similar things with lanthanide containing molecules, but I think experimentalists and theorists agree that these are very challenging atoms and molecules to work with. Let's get that. Just as a reminder overview of what part of the experiment we're going to be talking about. The main pathway molecule I'm going to be considering is this association pathway. You have to form your ultra-cold atoms, associated to get into this Feshbach state by magneto-association, and then transfer to the ground state. I'm going to be mainly focusing on this association stage in this talk. And so why this particular system? First of all, we know these two species. They're not the most common species, but there are clearly established pathways to cooling and trapping and using both of these atoms. And the pathway is for multiple isotopes of each. So deuterium has 7 isotopes, of which a few are friendly to the experimentalists. Chromium has, I think, 4 stable isotopes, of which at least 2 are fairly regularly used. And these include bosons and fermions of each species. So we've got all the mixtures we want. We've got both bose, fermi, fermi, and bose, fermi. Chromium has this 6 unpaired electrons, 5d and 1s electron. We've got this nice large spin. We have this predicted electron dipole moment from Mikhail of 1.2 dBi, which isn't as high as some, but it's pretty respectable for a high spin molecule. And certainly in contrast to the dysprosium systems and other lanthanides, the molecular structure is going to be incredibly simple. We just have this one potential because this deuterium is closed shell and this chromium is a spherical atom. So this simplifies my job certainly, and it certainly will make the experiment easier in certain ways. The important question is, are the correct interactions to actually form these molecules? A reminder about what a Feshbach resonance is. We have some interaction between quietly bound state and the scattering state. And when there's a coupling between them, we get features in the scattering. It becomes a magnetic Feshbach resonance when we can control it relative to threshold and tune it across, the threshold, and we get features in magnetic field. I'm going to be mostly focusing on this feature of the width. We're using renormalized width, but if you don't already understand this, you don't need to worry about it. So what's a coupling that we have in these systems? So anyone who's worked with Frye may be familiar with the spin-spin coupling in those systems. Might write it like this. We've got some fundamental constants out front. We have this classic 1/r cubed variation. And then we have some operators that couple the spins together and give us anisotropy. Don't need to worry about the exact form of these, but this is a fairly common form of the spin-spin. However, all our spins are on the same atom here, so we can't really use this form. This doesn't work. So we need to go to a molecular form of the spin-spin, which looks somewhat similar, but we now have the total spin entering here. So it's sort of the total spin coupling to itself. And we no longer have fundamental constants out front. We have to get some coefficient from electronic structure calculation. This form hasn't been seen in ultracold scattering as far as I'm aware, but it's very common in molecular spectroscopy. And this concept actually comes from the breaking of the symmetry. So you distort one electron differently from the others, and so the atomic symmetry that cancels this coupling to 0 in the atom means that it's non-zero in the molecule. So the results. So this is the interaction potential we have calculated. It's about 2,000 wave numbers deep and about 70-ish bound states. As I said, there's only one interaction potential. There's not a lot to discuss here. This is the calculated coupling. And in this strong interaction region, you can see it's getting up to sort of more than half a wave number. And so this isn't very strong overall, but when you're comparing it to, say, hyperfine couplings and other weaker things that you rely on in certain systems like these alpha single S, this is actually quite a decent sized coupling. This is going to be useful. So there's the single channel behavior. We don't know the depth. The electronic structure isn't accurate enough to give us a scattering length. So we have some variation. And it's actually going to be these red lines, these L equals 2 states, that are going to give us resonances. So we don't need to consider the full uncertainty. We can just consider one cycle here. And we can see that in this distance of variation, there's always going to be one of these L equals 2 states within the top 1 and a bit gigahertz. So there's always going to be a state that's close to threshold to give us a resonance, whatever the true potential. And so when I show results, there'll be a scaling, and that will be over a distance like this. And so we're just taking one slice out of this variation to stand in for the whole center. And so we then turn on the magnetic field. And we don't have any complicated structure, so all the states just split linearly. So this is two different positions of the bound state here. And the blue one is notable because this is the deepest the top resonance state can be. And so even when this state is at the deepest, there's a resonance. The first resonance comes out at just below 300 Gauss. So whatever your scattering, however unlucky you are, you will always have a resonance in the first 300 Gauss. And so here the resonance widths are calculated, very colourful plots. These are showing the same deep data, but with different things on the axis. And so this top one is showing, as you vary the potential, where your results are. And so these resonances are whatever the scaling of whatever your potential, whatever your scattering length is, you always guarantee the resonance that's somewhere up in this several hundred milligauss width range. And these are happening at magnetic fields of a few hundred Gauss again. This is showing the same data, but on a different set of scales. And we can see that as the field goes to zero, so the lowest field resonances are not going to be the best, even where they exist, because they go down to very small widths. And these peaks here at either end are associated with these peaks here, and those are to do with sort of near into the background scattering. This is just spend only 5 seconds here to say that the scaling with isotopes is very good. This is the same as the same plot we had earlier, but now we've got 4 different isotope combinations, just 2 isotopes of each species, and we can shift this pole and scattering wherever we want. So we've got a very good insurance against unlucky scattering events for this system. Very brief conclusions. The conclusion is that magnetoassociation seems very promising for this system. We should have a good number of resonances of a good width. And this might be a pathway towards high spin ground state molecules. Some brief acknowledgements from the group, like Yol Photo and Piotr, and various funding. Thank you.
Let's start questions.
Hi Matt, yeah, very interesting system. Maybe I missed it, so can you say something? What are the magnetic moments now of these molecules? I have a hard time.
So they're going to be spin 3, so they're going to be 3 electrons. I mean, you still have 3 unpaired electrons, 6 unpaired electrons. You'll just get the same spin as the atoms. It's like identical to chromium.
The lambda of R that you showed, it looked like it was decaying exponentially.
Yeah.
What sets the characteristic length scale of that exponential?
That's a good question. It's probably to do with the size of the orbitals. The electronic structure component of the collaboration might be able to answer.
So it's roughly the decay rate of the wave function of the chromium.
Yeah, it's basically a wave function overlap effect.
Are there any other questions? All right, with that, let's thank the speaker again.